that I showed, um, or it even tells us, whether a tactic is invalid. So a really common method for this is best first search, where you kind of enumerate different candidates and then kind of follow the best path. So that's some background, and what we were really interested in is whether we can introduce some kind of informal information into this process. So at the time, all of these formal theorem proving methods had been only trained on this kind of formal math data on the left. And so we were interested in whether we could have a model generate this kind of informal chain of thought prior to taking each step of the proof. And so why might you want to do this? Well, one is it gives the model some chance to plan out what it's about to do. In some sense, it could help diversify the search space. You go from just searching in this like formal space to the informal plus the formal space. And then there's been some cool, excuse me, theoretical work showing that introducing these chains of thought can actually lead to a generation system that's kind of more expressive. So it can actually solve harder problems. So those are some motivations. And what we propose to do this is an algorithm called lean star. Star stands for self-taught reasoner. And the basic idea is to learn to generate these thoughts by doing reinforcement learning. And so there's going to be two different stages, initialization and reinforcement learning. In the initialization stage, we just have a language model, basically take in the state and the step, and then it just generates kind of retrospectively some intermediate thought. And if we do this on a large data set, then we can fine-tune some initial model to basically generate these thoughts prior to taking a step of the proof. Then in the second stage, we want to actually generate these thought-augmented proofs with our model. And then we can use the proof assistant as a kind of really good reward signal because it could tell us whether these proofs are correct or not. So that's the basic idea. So what we need in practice is some method to generate the proofs that involve the thoughts, and then some reinforcement learning algorithm. So let me tell you about we did. What we found is this standard search algorithm, best first search. If you notice, it requires these kind of scores for ordering the different candidates. And what we found is it's actually kind of hard to get good scores for the thoughts. And so the standard algorithm didn't work that well for the thought augmented proving. So what we proposed is a new kind of parallel sampling method. So you could think of it as like sampling a full proof. But the difference is that if you run into a step that the proof assistant says is illegal, then you kind of try again. So it's a kind of interactive, like parallel depth first type of method. And then we need some reinforcement learning algorithm. What we did here is to basically try the simplest algorithm possible. And the algorithm is known as expert iteration or rejection fine-tuning or REST EM. And the basic idea is you generate proofs with your model, and then you just save the ones that succeed, and then add those to your data set, train the model, and then repeat the process. So of course, in the future, we want to use like better reinforcement learning algorithms. Here we're just using the simplest one. So the way you test these is usually on these math competition problems. So here's an example of this International Math Olympiad problem. So here's the problem in like informal math. And then here's the formal version that our model would get. And when you do this lean star procedure, then you see these improvements here shown on the right. So the red is the model that we start with. The black is when we do this initialization step. And then the gray is what happens after we run the expert iteration. And so you can see this kind of improvement from introducing the thoughts. Then we performed another experiment, and it turns out that if you just improve the underlying base model, then the lean star procedure was still working, but then you kind of shift all your performance upwards. So this was basically like during the project, there was better pre-trained theorem proving models, and then we tried lean star in it, and it was still able to improve those. An interesting thing is that this search algorithm also kind of benefited from scaling up the inference time search budget. So here on the x-axis, we have some units of search. It's related to like the total number of steps that you're generating. And then you could see that the green, the sampling with the thoughts, kind of keeps increasing, whereas if you don't have the thoughts, it wasn't as favorable. And then here's just some examples because you don't have to like read them again, but it's kind of fun to see. In gray, here's the kind of informal thoughts that you get. And so it has all these thoughts prior to like each step of these proofs. And if you were to read through them, especially like this one down here, it's actually doing some giving some reasoning behind this kind of step, which yeah, you kind of have to know formal theorem proving to appreciate what this is doing. And then here's just a long one, just because the long outputs look kind of impressive. So that's the basic idea of lean star, where we learn to generate these informal thoughts prior to each step of formal theorem proving. And one cool thing we found is that by introducing these thoughts, we were able to have better kind of scaling up of the inference algorithm. So that's the first part of the talk. Um, and yeah, maybe I could pause for questions on this section. And if not, yeah, you could also save questions till the end. Okay. Um, so next I'll go to the section on combining strong evaluation models with generation models at inference time. And again, we'll actually look at reinforcement learning again. And this is focused on this paper called Easy to Hard Generalization, which we just presented at NeurIPS in December. So in some sense, this formal theorem proving environment is pretty nice because we had access to this perfect checker. So you could like give it a proof and it tells you whether it's correct or incorrect. But in general, we often don't have access to this like perfect verification signal. So for a lot of tasks, ultimately we have to rely on humans. Like if we have some generation system, they're the ones that ultimately look and decide whether the generation is useful for their purposes. And so one issue with this is that it's really difficult to scale this either to a large number of a large amount of data, or interestingly to tasks that are just too hard for humans. And so kind of projecting forward, we're interested in developing generation systems that are kind of beyond human capabilities. So we have to come up with some approach to deal with this. So the kind of idea that we are looking into is what we called easy to hard generalization. So here humans can provide supervision on easy problems, but then we ultimately want to run our system and have it solve harder problems. So ones that humans can't kind of provide training data for or good supervision on. So in other words, the model has to kind of learn from this easy data and then ultimately perform well on hard data. And when you think about this, there's a kind of interesting idea here. So in particular, what we're going to say is that for the easy problems, you might have some input and then you also have some output, like a solution or an answer. And then the hard problem, you only have the input and you don't have any supervision. But then there's an interesting idea, which is like, what if at least some of these hard problems are actually easy to evaluate? Um, then what you could do is you could possibly learn some evaluation model. And at least if you generate some solution in this green area, then your evaluator model could tell you whether it's correct or not. So this is the kind of key intuition or idea that we're trying to explore here. And again, the idea is if you had this kind of easy to hard evaluator, then you could use it in even like the simple inference time strategy. So this one here asks the generator to generate multiple outputs. And then if you have a good evaluator, it could just like pick the best one. So what we need to actually realize this is we need some method for training this evaluator. And then we need some inference strategy that actually works well for combining the evaluator with the generator. So here we kind of define easy using the setting of math. We also tried on code as well. And so we took this data set, the math data set, and they had the problem separated into these different difficulty categories. And so our easy setting is going to be level 1 through 3 problems. And there we assume that we have both the problem and the solution and the answer. And then we want our model to do well on the level 4 and 5 problems. And there we assume that we don't have the kind of human solution or human answer. So what we do is we train an evaluator model. And the evaluator model kind of combines two different ideas from previous work. So first, there's an idea of an outcome reward model or evaluator model. And so these take in like a full solution and then try to predict whether it is correct or not. Then there's another type of evaluator or reward model called process reward model. These take in just like the partial steps so far and then try to predict whether it's valid or not. So we tried something kind of simple, which was to just train a evaluator on both kinds of data. And it turned out to work a bit better than training it on either just the outcome or just the process reward. But the new thing here is not necessarily the reward model. It's just the idea that we're only training it using the easy data, and then we want to see how well it works on the hard data. Okay, so then the inference time method, we again used a method from previous work called weighted majority voting. So here you generate many solutions with your generation model. Then you come up with a score for each solution using the evaluator. And then you basically group the solutions by answer, and you choose the answer that kind of has the highest total score. And so, yeah, this is called like weighted majority voting or weighted self consistency. So here's a kind of interesting, here's like really one of the main interesting results. So what this is showing is we have our evaluator model that was only trained using easy data. And then we incorporate it into the inference algorithm and we look at the performance on the hard data. And you can see that when we incorporate the evaluator with the weighted majority voting, it's actually able to kind of improve the performance on these hard problems, and it's actually still monotonically improving as we sample more. In comparison, if we like just use the model on its own, so without the weighting, the majority voting, then the performance is lower. So it's really showing that introducing the evaluator is um, giving us this performance gain. And then this also carries over to just all problems. So it doesn't just improve on the hard problems. It also improves on the easier ones as well. Um, Another interesting thing is like how large your generator has to be versus how large the evaluator has to be. So we did some experiments with that where we varied the size of the generator and the evaluator or reward model. And I think one of the interesting ones is this third one here. You could see that even when the reward model was 7 billion and the generator was 34 billion, the weighted voting, kind of the evaluator was still helping over not using the evaluator. So that would be the majority voting baseline. Um, and then we were kind of interested in whether you could use this evaluator as a reward for reinforcement learning. So here what we want to do is, again, we don't have any answers for the hard problems. So you can't just check whether the answer is correct for your reward. What we do is we use our evaluator as the reward function and then try to do reinforcement learning. And kind of intuitively, this is simulating the setting where you want to, yeah, do reinforcement learning on problems that you don't even have answers for, which might be something that we want to do in the future. And the kind of interesting result here was that our model um, actually did better than a model that was fine-tuned on both the easy and the hard problems. So again, if we kind of cheat and take the human solutions to the hard problems and just use the supervised fine-tuning, then our reinforcement learning model was actually doing better despite not having any human supervision on the hard problems. So that was a kind of cool result in that direction. So that was the second part of the talk on ways to combine these strong evaluation models with the generation models and actually get some degree of generalizing to harder problems. So in the final section, I'll talk about thinking kind of systematically about scaling up inference time compute.
Just before we go ahead,
Mhm.
I just had a couple of questions on this part. I
Yeah.
just want to go back to the figure where you were introducing the easy and hard problems and the circle in the middle with easy to evaluate problems.
Mhm.
So probably I don't know the math data set as much, but I'm trying to understand um, what's the peculiarity and how the math problems fall into each of these different categories here. Like what does it mean to say that this math problem is an easy to evaluate problem but hard to solve or solve problem? Yeah.
Yeah, yeah. Yeah, so the easy to evaluate, we don't actually know. We don't know if problems are easy to evaluate or not. That was just our kind of hypothesis.
Okay.
But then the easy and the hard problems are labeled by humans. So when they were building the data set, they, for instance, took it from math competition problems.
Hmm.
And so sometimes like different kinds of competitions are easier than other ones. But then ultimately they have a human kind of give it a 1 through 5 difficulty score.
Okay.
Mhm.
Okay. And then just on the last slide where you introduced how doing PPO with the reward model was better than doing a whole SFT.
Mhm.
Yeah, maybe I'm just trying to get intuitions of why and how, because I'm assuming that when you're fine-tuning on all the XY, the Y is actually the ground truth itself, which should probably have the perfect signal. But the RL, the reward model can just like it may not have the perfect signal all the times. There might be some noise in it. And I'm trying to get an intuition because the gains look very significant. And do you have any thoughts there?
Yeah, yeah. Yeah, that's a great question. Um, so yeah, I guess if I had to give some argument, it maybe be two different things. So first, obviously the performance isn't going to 100%.
Mhm.
So on some problems, the evaluator is probably really bad, and you're kind of doomed for the reinforcement learning. But then maybe it is beneficial on um, some other subset. And for this other subset, I think the difference could be that it might be easier for the model to learn from its own generations versus from the human solution. So the human solutions is just like one way to solve it, and it's written by a human. But maybe if you have the model generating multiple ones and then you kind of select the best one, then it's easier to kind of just um,
Mhm.
like even like sharpen its distribution towards those.
Sure. I think Shaching also has a question. Shaching, you wanna?
Yeah, thank you. So I have a question similar to Tammy's question about the set of questions that can be hard to solve but can be easy to evaluate. So I wonder how frequent is this kind of question in like real world and especially less formal reasoning. Because I can imagine maybe in mathematical reasoning, the whole reasoning has to be formal, and then if there's one single error in each of the state, then probably the evaluator can judge that is incorrect. But in real world reasoning, like say reasoning in social situations, probably even the reasoning itself is not super formal, and then there are probably some jumps within the reasoning. The reasoning probably needs some background knowledge. Etc. So what I'm saying is it's probably also very difficult to evaluate it as well. Do you think that set of questions also are very common in other types of reasoning?
Yeah, that's a great question. And yeah, one of the things we're interested in right now is kind of thinking about these kinds of things for broader domains. And so I do think that like in some cases, it's not necessarily easier to evaluate than to generate. Um, Even with some types of code, the model would have to like literally like internally run the code to tell whether it's correct or not. And then similarly, yeah, in some domains you might have um, reasoning, which is, or you might have like a subjective type of task, or you might not have something which is as easy to decompose into multiple steps. Um, I guess what we've been finding so far is that, um, yeah, if your task can be decomposed into multiple steps, and the errors are kind of localized, then yeah, you might have some hope for that. But yeah, I think it's still an ongoing area. Like now that we've kind of demonstrated this in math and in some types of code, seeing how it applies to wider domains.
Okay, thank you so much.
Hmm.
Hi. I also have a question.
Hmm.
Like, I'm wondering how can you define a step in a reasoning process? It seems a little bit tricky and non-trivial since if you let the granularity be too fine, and then it will be inefficient, and if you do not decompose it, and then one step will be too difficult to solve.
Hmm. Yeah, yeah, that's a great question. So I think nowadays people are starting to use a model to uh, decompose some trajectory into different steps. So even with math problems, yeah, you might have like multiple sentences that are kind of part of the same logical thought and or logical, step of reasoning. Um, so I agree. Yeah, I would say one thing is you could try to have a model decompose it. Another is if you're interacting with some environment, then maybe you have some neater notion of like, okay, I take some action the environment gives me something new, I think, I take some action, and so on. So I do think that, that covers some set of domains, but then, yeah, again, in full generality, there's a lot of cases where you can't break it down as easily.
Yeah, I see. Thank you.
Mhm. Okay, cool. Maybe let me go to the next section, just to make sure I get through all the content, and then happy to take more questions. The questions have been great, so thanks. So here I'm going to focus on this paper called Inference Scaling Laws, and this was recently accepted to iClear. So I guess in the previous part of the talk, we showed that increasing inference compute, so sampling more from the model in this case, was increasing the performance. And here we were kind of interested in thinking about the various aspects of inference compute and trying to come up with like the best configuration for different compute budgets. And then we were also interested in kind of what happens if you were to take this arrow to infinity. What are some of like the limits of these inference time methods? So in particular, you can look at one way of defining inference time compute, which is it's determined by the size of a model and the number of tokens that you're generating. So for example, in the strategy I was talking about before, again, you have like a model of a given size, and then you generate these multiple outputs, and the total compute is based on the size of the model and the number of tokens. And so a question becomes, in practice, we have some fixed compute budget, and we want to know like what is the best configuration for our compute budget. So for example, should we actually use a smaller model but generate more tokens, or use a larger model and generate fewer? Kind of what gives us the best returns? And so this is interesting for a few reasons. One is sometimes you're in a really compute constrained setting, like a phone. The other is, maybe you have a really large inference budget and you want to just know like what is the best strategy that I can use and kind of how far can it go. So we look into three different questions here. One is, should I use a small model again and generate more, or a large model? Can we design strategies that are better than the ones we've seen so far in the talk? And then again, how far can these kind of take us? And to do this, we develop what are called inference scaling laws to help answer. So the first question is, given some fixed compute budget, should I use the small model and sample more, or the large one and sample less? And the way you could look into this is to kind of create this kind of frontier. And what happens is you can, for a given inference strategy, try different model sizes. And then you can look at, for a given compute budget, how is each model size performing? And at any given compute budget, you'll have some compute optimal model. So that's what's shown in green. This is the kind of compute optimal frontier. And so ideally, you want some configuration which is on this frontier. Here we're showing error, so kind of lower is better. So we did this in practice. And what we did is, tried various model sizes and then various compute budgets. And again, you adjust the compute budget by like generating more. And this is again on a math data set. This was GSM 8K. And you can see this kind of interesting frontier forming. So in particular, if you have like a really small inference budget, then it turns out to be beneficial to actually use not the largest model, so like even a small model or a medium-sized one, and generate more with it. And then also, if you kind of want to get the best performance possible, then if you have like an unlimited inference budget, you can see that using the large model is still optimal. So then we looked into can we also vary the inference strategy? So in the plot here, I was showing the majority voting that I mentioned. And what we did is design this tree search algorithm. And the idea was to try to do better than the parallel sampling when we take both cost and performance into account. So the idea here is kind of intuitive. It's called rebase or reward balanced search. And so what you do is you take one of these process reward models, and then you expand this tree using some expansion budget. And the way you choose which nodes to expand next is you just look at the process reward model's scores. So for example, here, this kind of path got a high score, so we'll allocate more of the exploration budget to it. This one got a medium score, so yeah. And then this one said 2 + 2 = 5, so maybe we don't explore that one further. And then you keep doing this for multiple steps, and you eventually get full solutions. And what we found is that here we were trying this rebase algorithm. We were trying the sampling-based majority voting. And we were also trying this Monte Carlo tree search, so this more kind of sophisticated tree search. And we found that the rebase algorithm could actually be kind of Pareto optimal. So if you look here, like at each inference budget, the best configuration involved using rebase, either with a 7B model, or to get the best possible performance, you would use the rebase with the larger model. And so this was kind of cool because it said that there's some hope in designing better inference strategies that give you better trade-offs. And then also, you can see that this 7B model is most of the time actually outperforming the 34B model. And in particular, if you just use the sampling algorithm, then rebase actually just gets better absolute performance than the 34B with sampling. And so this was kind of cool because it suggests that a good inference strategy can kind of unlock more capacity from the smaller model. And then finally, it's just also important to take into account the cost of inference. So what we found is that there were several works looking into using Monte Carlo tree search. But Monte Carlo tree search turns out to be a kind of expensive search algorithm. So when we compare it on an equal cost basis, you can see here that it's not performing too favorably. And then finally, we asked the question, what if you had infinite compute? And so here we studied this weighted majority voting algorithm. And we had this kind of interesting theoretical result. And it was looking at what happens if you scale up the number of samples to infinity. And we basically showed that the accuracy that you get converges to the accuracy shown here. And there's a lot of symbols, but it's a kind of intuitive idea. It's the accuracy that you get if you kind of sum over all of the possible paths to a given answer. Kind of like marginalize out these intermediate reasoning paths. And when you look at this, you can get some interesting takeaways. So one is it's saying that our accuracy is ultimately going to converge to this accuracy here. And so basically, like even with infinite compute, you're ultimately going to converge to, some accuracy. And if you look at what the accuracy depends on, it depends on the reward model, or your underlying generator. And so if you want to kind of improve the upper bound on performance, then this shows very clearly that you can benefit from either improving your reward model or your evaluation model, and or improving your generator with a better model or a better algorithm. So it was a kind of nice result, and at least for me, kind of clarified some things that are going on with these majority voting methods. So that was the third section of the talk. And so that also concludes the talk. So the theme was reasoning with inference time compute. And I talked about training models to think. That was the Lean Star project, incorporating the strong evaluation model, and then notions of inference scaling laws and compute optimal inference for finding or designing um, uh, inference methods based on like cost and performance. And so, yeah, all of this work was done with these amazing collaborators. Lean Star was led by Hao Han, who was a visiting undergraduate student from Tsinghua. Jiuqing, who is a PhD student at CMU and is also now at OpenAI. And Yang Zhen, who is also a visiting undergraduate student. Also, just another shout out. We had a survey paper on these different inference time algorithms. So we kind of go over the different common patterns that have been developed and survey them. And we just had a corresponding tutorial at NeurIPS. So if these kinds of things are interesting, you can check out the materials there. We posted basically everything online. So that's it for my talk, and yeah, I'm happy to take any additional questions.
Hi, I have one question about the inference scaling law. Like in the
Mhm.
end, there's a limit when the number of sand costs go into infinity. I'm wondering what is the convergence rate to that limit? I think that's important because it somehow shapes the scaling law curve, right?
Yeah, yeah. That's a good question. So we do also have the rate in the paper. Um, I don't want to miss-say what it is,
All right.
but you can check out the paper
All right.
to,
All right.
yeah,
Thank you.
to see that as well.
Okay, so yeah, I think we can take some more questions now. We have a few minutes. So if anybody has any questions, please raise your hands or you can just directly start speaking. One quick clarification question I had, I think this is regarding the third project when you initially mentioned about the cost. You mentioned the tokens. I'm wondering if like are they just the output tokens that the model is trying to generate, or is it all the tokens that the model takes as part of the input as well?
Yeah. So we're just considering the output tokens.
Okay.
Mhm.
Because I think like one of the other dimensions of looking at this is also, I don't know, I did see a couple of papers about this, but in terms of demonstrations and in context learning and like how you can keep increasing it, but that also uh, affects the capacity of the model to interpret and understand, and like it also increases the cost. Like if you just have a lot of demonstration examples. So I think yeah, that's where I was heading with respect to that. That's also probably another dimension when we are considering inference time compute.
Yeah, yeah. Yeah, I think there's a few interesting things to expand upon. So yeah, one that you mentioned is to actually vary the inputs as well. So here we were just using, we were actually using fine-tuned models. So we just give them the problem. Another is here we're kind of picking a method for the entire data set. Whereas I think what we ultimately want is like for a given input, choose the inference strategy.
Yeah.
Or even like as you're generating the input, you might like adjust the strategy. So I think that kind of thing is is pretty interesting as well.
Yeah, I think that sounds more intuitive as well, because like as humans as well, if we have easier problems, we probably choose a faster. We don't need to sample so much. We know the answer should be right, and yeah. I think that sounds like a good direction.
Yeah.
Hey, can I ask a question?
Mhm.
It's a sort of, I hope you don't take it as a pointed question. I'm genuinely curious about your outlook of the research and the field, because I think the work you're doing is very cool. Especially taking the first project that you have and contrasting that a bit with the last project that you presented. The first project definitely is introducing some complexity to the generation pipeline that is increasing compute, leading to better performance in general, right? Now we're in this interesting time where it seems like still when you keep scaling things that we cannot achieve usually in academic setups, but that they're trying to achieve in industry, then maybe the outlook is we don't have to come up with more and more complex solutions. Like you can achieve the same thing if you're going into industry and you have these resources, and you can just leverage the compute itself and you can reduce the complexity of the solution on its own. So I was curious, how do you see, do you think there's this value that we can add in trying to achieve similar performance by investigating these approaches to solutions? What is your outlook? How long do you think people are going to use these more complex solutions? Who is going to use these more complex solutions? I hope you're getting what I mean here.
Yeah. So I think these are great questions, and it's a kind of big question. So maybe let me break it down into a few parts. So the first part that comes to mind is sometimes, especially with the formal theorem proving that I mentioned, we're actually interested in like building different types of tools for like mathematicians or make it easier to use the formal proof assistants. And so there you have actually kind of two extremes that are interesting. So one extreme is people want things that can literally run on their laptop, and they don't actually want the best possible performance. They just want it to be like so fast and not necessarily need an internet connection, and it just like becomes part of their workflow. The other is you could imagine that maybe there's some proof in your project, and you just like send it to the machine learning model, and then you come back the next day, and it's actually like created some non-trivial proof. So there you could have a completely different method, which is maybe like spending a lot of computation and getting some result at the end. And so I think both things are pretty interesting. And then I would say with the complexity, I would say, yeah, I think the progression of methods is that we ultimately try to look for simple things, and that allows us to build on top of them. And so I think maybe the simple idea here is that the community is still exploring this like knob that we have at Inference-time, where we can just like add more compute and get better performance. And for that, I'm kind of hopeful about academia, because although we might not be able to get the absolute highest performance on a benchmark, I think the advantage we have is like being able to try crazy things and kind of show things at a small scale. And I do think some of this can at least be, conceptually shown at smaller scales. And then maybe it's like refined or scaled up in industry.
So if I may ask a
Yeah.
follow-up on that. So that is based on the assumption that we can show things on a small scale and they do scale up in the same way on a large scale. Like, is that the hope?
Yeah, I guess, for any given idea, it's not always the case that it scales up, so it's still difficult. But I mean, one of my favorite examples is like the DPO algorithm. That was kind of shown for the first time on relatively small data sets, and then it turned out to be able to be scaled up and used in other places. And then sometimes, aside from all this, sometimes we also just want to understand things better, I guess. And so, I don't know, my own understanding, hopefully others in the community, becomes a lot clearer when we have, yeah, different things like, to use the example in this talk, like the inference scaling laws. There's been a lot of cool work by others. Again, it could be at a small scale, but it's kind of showing new concepts or new understanding.
Thank you.
All right. Do we have any other final questions before we end the talk?
Hi, I have a quick question. I'm not sure if you already explained this before, but I just want to double check. Before you mentioned about those hard problems but easy to evaluate, have you visualized those? I'm still, because I may not be very familiar with those, but I actually have a hard time understanding what kind of questions are those, because it's hard to imagine hard problems but easy to be evaluated. What are the characteristics of these problems?
Yeah. Yeah. I don't know if I have like a systematic evaluation of it, but like one example is you know, in part of a solution, maybe it does some computation incorrectly, and it's kind of easy to observe that it's incorrect.
I see.
Whereas like coming up with the strategy to kind of take that strategy and perform the computation is the kind of hard part. So yeah, I think especially in problems where maybe it requires a lot of creativity to come up with the strategy, but then when you see the result, you can kind of tell whether it's incorrect or not. That's kind of, yeah, how I think about it.
I see. Because my bias before was thinking if it's a hard problem, so it should be the solution should be complex too, should be hard too. But okay, I see. Okay.
Yeah. The other thing is, if the solution decomposes into these steps too, and then the error is, it could be in a really long solution, but then if it's localized, then there's some hope that, you know, maybe it's easy to identify this like one step in the complex solution.
Mm-hmm. So yeah, thanks.
Even if you're going into creative writing or painting, like any sort of creativity, right? Like I would be terrible at creating that myself, but I can judge whether a painting is good. Like I feel that would also translate well.
Yeah, exactly.
Cool, makes sense. Okay, yeah, we are right about time. So let's thank our speaker once again. Everyone, thank you, Sean, for giving us this talk and sharing your brilliant insights on this topic. And yeah, please feel free to reach out to Sean in case you still want to like know more about their works. Yeah, thank you. Thank you for everyone for attending the talk as well.
Okay, thank you. And yeah, thanks for all the great questions. This was a lot of fun.
Awesome. Thank you so much. And yeah, hope to see everybody else next week for the next talk. Yeah, thank you.